finally, I want to think about the case of multiple slits. So multi-slit interference. And let's consider the case of 4 slits. So we've got our barrier with 1, 2, 3, 4 slits in it. I've got my observation screen over here. And the basic principle is the same as what we saw before, that in order to see a bright spot at some point here, I need to have constructive interference from the light that's being emitted from all 4 slits. So let's consider, let's say, this point here. And I've chosen that point so that the path length difference between these two rays, we're measuring our angles relative to the horizontal as before. So this path length difference would be d sine theta, where d is the distance between the slits. And let's label our slits, A, B, C, and D. There's 4 of them. So now, if I draw this line, you can see that this path length difference in the approximation that we're using of this right triangle is just twice this. So this would be 2d sine theta. So let's say that maybe in terms of the 2-slit pattern, this is the m equals 1 point. That is to say that d sine theta is equal to 1 times lambda. So I have a path length difference of 1 wavelength between slits A and B, but between slits A and C, there's just 2 wavelengths difference. So that means that A and C would also be in phase. And similarly, D would be 3d sine theta, so that would have an extra 3 wavelengths, but it would still be in phase. So all 4 slits would be in phase whenever the top 2 are in phase. So we see that the positions of the maxima are the same. The positions of the maxima in our interference pattern are still determined by d sine theta equals m times lambda. But now let's think about the effects of destructive interference. So maybe I can fit this on the same piece of paper. I keep on turning it sideways a little bit, straighten it out. So same pattern of 4 slits. A, B, C, D. Here's our observation screen. Now I want to consider a point that is actually let me start a whole new drawing so I can fit everything on better. There's our 4, and let's say that this is the point that we were just talking about, m equals 1, where I had full constructive interference. The straight ahead direction, that would be about here, m equals 0. Let's consider the halfway point, m equals 1/2. So there I would have a half a wavelength difference between slits A and B. So A and B are going to cancel. And I would also have a half a wavelength difference between C and D. So C and D will cancel out. So here A cancels B, and C cancels D. So far, this is looking very similar to the 2-slit pattern, where I have a minimum of interference, 0, that is to say 0 intensity at m equals 1/2, and full intensity at m equals 1. But now let's think about this point, which we could maybe call m equals 3/4. So maybe I'll use a different color pen for this. So if I think about the paths between A and B, that path length difference would be 3/4 lambda. So I'm not quite sure what to make of that, but now I know when I add c in, that the path length difference between A and C will be twice this. That is, this will be 1.5 lambda. So 1.5 lambda, that's going to give me destructive interference between A and B. So at this point, A cancels C. Sorry, I said destructive interference between A and B. I meant between A and C. A is going to cancel C, and if A and C have a path length difference of 1.5 lambda, then B and D will have a path length difference of 1.5 lambda. So B is going to cancel D. So that's also going to be a minimum of the interference pattern. I've not quite drawn things to scale again, but if we think about this point at m equals 1/4, that would mean a 1/4 wavelength difference between A and B. So I'm not sure what to make of that, but if it's a 1/4 wavelength difference between A and B, that means it's a 1/2 wavelength difference between A and C. So again, A is going to cancel C, and B is going to cancel D, because B and D would be separate by a 1/2 a wavelength. So I can show that more easily from these bottom ones. So C and D, their path length difference, that much, that would just be a 1/4 of a wavelength, but the wavelength difference between B and D, that would be a 1/2 a wavelength. So B is going to cancel D, and if B cancels D, then A is going to cancel C. So I get, when I put this all together, the total interference pattern is going to look like I have a maximum at m equals 0. The intensity goes to 0 at m equals 1/4. It recovers a little bit, but then it has to get to 0 again at m equals 1/2. It comes back up a little bit, goes to 0 again at m equals 3/4, and then it gets back up to a full maximum at m equals 1. And the whole pattern, of course, is symmetrical. So, why is this important? Let's now think of a real experiment in spectroscopy, where I'm trying to determine how much light is coming out of some source. Maybe it's a star, for example, at various different wavelengths. And perhaps I'm trying to separate out light that is red from light that's blue. Let's do that same experiment twice. First with a 2-slit interference experiment, and then with a 4-slit. So here's our 2-slit pattern, and red light has a larger wavelength than blue light. So we have m lambda equals d sine theta, or sine theta equals d over, equals m lambda divided by d. So red light has a big lambda corresponding to relatively large sine theta. So that means that the 2-slit interference pattern for red light would look something like this, where here's the m equals 1, m equals 0, m equals minus 1. Now blue light has a shorter wavelength, so its pattern will be compressed, as we talked about in a previous concept test. The m equals 0 peak is at the same position, but the first minimum is at a little bit lower angle, and the next maximum for the blue would be at a lower angle also. So the overall effect would be something like this. So you can see that I can start, so the m equals 0 is the same for both. I can start to separate out the blue from the red by looking at the m equals 1 or the m equals minus 1 peaks, but there's a lot of overlap. Let's contrast that with what happens when we use the 4 slit. There's our 4 slit. And now let's think about the pattern for the red light. Here's the m equals 0 peak. There's a couple of wiggles, and the m equals 1 peak. And on this side, a couple of wiggles, and the m equals -1. That's the red. The blue, so this is, let me label the peaks again. So this is m equals 1. This was m equals 3/4, m equals 1/2, m equals 1/4, m equals 0. So for blue, everything is kind of compressed, so it's going to hit this m equals 1/4 a little bit sooner, hits the m equals 1/2 a little bit sooner, rises up here, and then it's got to start coming back down again. And so you can see you get much better separation between the red peak and the blue peak. And so that's going to allow you to measure more quantitatively the amount of red light and the amount of blue light that you've got. You can maybe see that if I doubled the number of slits from 4 to 8, the effect would be even more extreme. So if we compare these two patterns, the first 0 in the 2 slit pattern is at m equals 1/2. The first 0 in the 4 slit pattern is at m equals 1/4, and that defines the width of this peak. And each of these peaks has the same angular width. So if I go to an 8 slit pattern, the first 0 will be at m equals 1/8, meaning that the peaks will be, again, a factor of 2 smaller. So the more slits I can have, the narrower the peaks will be, and the better I will be able to resolve different wavelengths. So this leads to the idea of a diffraction grating. Diffraction grating. Can't even spell it. Diffraction grating, which is just as many slits as you can get packed together like so. You shine your light on it as usual, and let's say I'm shining light that contains some blue and some red. Now on my screen I'm going to get very sharp peaks, because maybe instead of 2 slits being illuminated, I perhaps have 800 slits. So I'm going to have very sharply defined peaks like so. And again, there's a superposition or a multiplication of this multi-slit pattern by the single slit interference pattern. So the red might look something like this, and then the blue, the peaks, there's still the same central peak, but these side peaks come, I'm exaggerating a little bit, at significantly different angles, so we can really separate out the light very, very well using a diffraction grating. But again, the position, the angles of the maxima are still defined by the same formula, that d sine theta is equal to m lambda, where d is the spacing between your slits.